Hello. This is going to be a run-through of a very common type of problem that you will see involving not only stoichiometry, but also limiting reactant, solution concentration, percent yield, and predicting precipitation. Okay, so our problem here says we have 123 milliliters of a 1.00 molar sodium chloride solution is mixed with a solution containing 25.0 grams of mercury 2 nitrate. And the question says, what is the identity and mass in grams of the precipitate formed? Okay, so like any stoichiometry problem here, we have to start with a balanced chemical equation. So I'm going to start writing here. Well, sodium chloride is a pretty simple formula. I mean, everyone kind of knows that one, NaCl, okay? But that comes from the sodium ion, which is +1, and the chloride ion, which is -1. So a 1-to-1 ratio here means we have 1 sodium ion to 1 chloride ion. And it says that it is a solution, okay? There's that word solution. So we know this is aqueous. This is being mixed with mercury 2 nitrate, okay? So in order to write the formula for that, we need to think, what two ions are we combining here? Well, we have mercury 2, which is Hg2+, and we have nitrate. Nitrate is one of those polyatomic ions, NO3 -1. Okay, so we don't have a 1-to-1 relationship like we had here with sodium and chloride. We have a 2-to-1 relationship, which means we need 2 of these nitrate ions to balance out this +2 charge and neutralize this compound. So we have our formula HgNO3 in parentheses 2, telling us to have 2 nitrate ions. Okay, this is also a solution, tells us right here. So this is aqueous as well. Okay, so those are our two reactants. So we need to figure out what are the products being formed here. All right, so this is 2 ionic solutions reacting. Okay, so this is going to be a double replacement reaction, double displacement reaction, whatever your teacher may say. And we can think of this as recombining these 4 ions into 2 new compounds. Okay, the 2 positive ions will recombine with the other negative ions. The 2 cations that we have here will recombine with the opposite anion. Okay, so another way to think of that is we're going to recombine outside 2 and inside 2. And what compounds do we get when that happens? Well, we're going to get sodium and nitrate combining. Okay, we have a 1 + 1 and a -1. So we have a 1-to-1 relationship here. So NaNO3. I'm not going to bring over this 2, because that 2 is there because we need 2 of these ions to balance the +2 on mercury. Over here, we only need 1 of these ions to balance the +1 on sodium. Okay, next, our other product is the inside 2. We have mercury 2 chloride. Okay, so mercury 2 is a +2, chloride is a -1, so we need 2 of these chloride ions to balance out this +2 charge. So our new formula here is HgCl2. And now I need to apply some solubility rules. Okay, which, if any, of these 2 compounds are soluble or insoluble? Okay, so first rule of solubility is that group 1 metals, nitrates, and ammonium ions make things soluble always. Okay, and in this first compound I have a group 1 metal, sodium, and I have a nitrate ion. So this is soluble, AQ. Next we have mercury 2 chloride. Okay, so we don't have a group 1 metal, we have this heavy metal here. Group 1 metals, these ones, make things soluble. Mercury is really far from there. Okay, we also have chloride ions, which are not insoluble, but they tend to be soluble. But things like heavy metals, mercury, silver, lead, tend to make things insoluble. So this is going to be a solid. All right. Last thing we have to do this equation is balance it for stoichiometry. So we just take a quick look. I have a sodium, I have one sodium and one sodium. I have one chloride, I have two chlorides over here. So a 2 up front will fix that. That changes my sodium. Now I have two sodiums here. I need a 2 in front of sodium nitrate to balance that out. Now let's continue. Mercury, one mercury on each side. Two nitrates here, two nitrates here. We are balanced. Okay, so now I can start doing my stoichiometry. Okay, so in the problem, I'm given amounts of two of my reactants. Okay, both reactants have amounts. Okay, so we need to compare those using moles and our mole ratio given in the equation. So I need to convert 123 milliliters of a 1 molar sodium chloride solution to moles of sodium chloride. Okay, and we can do that with moles equals concentration times volume. Okay, so for sodium chloride, moles equals concentration times volume, we have 1.00 molar. Remember, molar is moles per liter. So let's write that out. And our volume is 123 milliliters. We want this in liters, so it's 0.123. To get from milliliters to liters, just move your decimal place 3 places to the left. Okay, so that cancels out liters, and we can see that we do end up with moles here, and that is perfect. That's what we want. So 1 times 0.123. We have 0.123 moles of sodium chloride. Mercury 2 nitrate, okay? Different story here. We don't have concentration volume. We have mass, all right? And mass is pretty simple to use because moles equals mass over relative molar mass, okay? So our mass is 25.0 grams. We need the relative molar mass of mercury 2 nitrate. So mass of 324.61, and that is grams per mole. All right, so the grams cancel here, and we're left with 1 over a mole in the denominator, which means we have a mole. All right, so our moles of mercury 2 nitrate is 25 divided by 324.61. We have 0.07703 moles. So I'm going to write that up here underneath mercury 2 nitrate, 0.07703 moles. So now I need to compare these two moles to figure out which one's going to run out first. That's limiting reactant stoichiometry. And it is a complex idea. It usually looks complex on paper, but it is really simple. All I need to do is convert one of these into the other one using the mole ratio from the equation. And then I compare those two numbers. So I usually convert the first one. So we have 0.123 moles of sodium chloride. Okay, I'm going to multiply this by our mole ratio of mercury 2 nitrate over sodium chloride. So mercury 2 nitrate is a 1 mole over the 2 moles of sodium chloride necessary. So I'm going to multiply this by 1/2. And we end up with 0.0615 moles. All right, so when I divide this by 2, I get this. This means that I need 0.615 moles of the mercury 2 nitrate in order to react all of this sodium chloride. Since I have plenty of mercury 2 nitrate, I have more mercury 2 nitrate than I need, that means that the mercury 2 nitrate will be in excess. There will be some left over. That also means that my limiting reactant is the sodium chloride. So I'm going to write LR next to it somewhere just so I don't forget. And I'm going to circle that number because that number right there is the number of moles of my limiting reactant that I have. And I'm going to start all of the rest of this problem from that number. Okay, remember in normal stoichiometry, we find moles of our reactant first. That's the first thing we do. Very similar here. I have found moles of my limiting reactant. Just took a little bit longer to get there. So I can start from there, and I want to figure out, again, the identity and mass in grams of the precipitate formed. We have already found the identity. It's going to be mercury 2 chloride. Okay, that's the identity. ID. Okay, we need the mass in grams. Okay, so from here on out, it is your basic stoichiometry problem. We're going to start with moles of our limiting reactant, 0.123 moles of sodium chloride. We'll multiply by a mole ratio of my precipitate over my reactant, so 1 over 2 again, 1 mole. Mercury 2, I always try and write M. Mercury 2 chloride over 2 moles of sodium chloride times, now I need the molar mass of my mercury 2 chloride. So we have the molar mass of mercury 2 nitrate. We need the molar mass of mercury 2 chloride. So it gives us 271.49 grams of mercury chloride for every 1 mole of mercury 2 chloride. All right, so checking my units here, well, moles of sodium chloride cancels moles of sodium chloride. Moles of mercury 2 chloride cancels moles of mercury 2 chloride. I'm left with grams of mercury 2 chloride, and that's what I'm looking for exactly. So I know my setup is correct. I just have to do some math. And when I multiply 0.123 times 1 divided by 2 times 271.49 divided by 1, I get 16.696 grams. Okay, so the last thing I need to do for this part of the problem is to consider significant figures. All right, if I look in the problem, all right, I want to look for, I used this number. This number came from the concentration and volume of sodium chloride. So I look up in the problem and I see that the concentration had 3 significant figures, 1, 2, 3. The volume also had 3 significant figures, 1, 2, 3. So my answer needs 3 significant figures. Because I'm multiplying and dividing, my answer has to have the same number of significant figures as the given, here and here, with the fewest number of significant figures. They both have 3, so my answer needs 3. So I start counting from the left, ignoring any zeros to the left of this first non-zero digit. And I count 1, 2, 3. The 6 here, the tenths place, is where I need to round my answer to. And the 9 after the 6 rounds this to 16.7 grams of mercury 2 chloride. All right? Always units, species, and significant figures in your final answer. And then go ahead and give it a box or a circle or something, just so whoever is grading this or reviewing this can find it easily. We want to look at some percent yield. And if I adjust my camera here, a student performs this same reaction in a laboratory and finds that after filtering and drying our precipitate, okay, it has a mass of 12.21 grams, and we want to know what's her percent yield. Okay, so percent yield is a great way to tell how efficient a reaction is. Every reaction has its own kind of efficiency. Very few of them go to anything near 100%, just because that's the nature of the world. We always get mass loss somewhere. Anytime we're transferring containers, or if our chemicals weren't exactly pure, or if we have a lot of different things can cause errors here. We don't need to worry about those so much just yet. We just want to know, what is our percent yield? Okay, it's probably going to be less than 100%, because like life, we rarely ever get 100% of our reaction. Okay, rarely ever do we have 100% of our limiting reactant used up before the reaction stops. So we're going to take a look here, and percent yield is a simple calculation. Percent yield is equal to our actual yield divided by the theoretical yield times 100%. Okay, and this should look familiar. It's your basic percentage calculation. Okay, it's the part over the whole times 100% to give it that percentage. Okay, so these two terms here might be new for you. They might not. Actual yield is what is actually measured. Okay, this implies that we have done the reaction, we have been in the lab, we have done an experiment, and we have measured the actual mass of the product. Okay, so this sometimes you'll hear it called laboratory yield, so lab yield, or experimental yield. Okay, they're all the same thing. Okay, in this case, our actual yield, she did this in the lab and found that the precipitate has a mass of 12.21 grams. So our percent yield, can't spell, 12.21 grams divided by our theoretical yield. Well, in theory, that is our paper. That is the math. That is on paper ahead of time, given just the amounts of reactants we have. Okay, the theoretical yield is our calculated yield. This is what it should be, and we calculated that at 16.7 grams. So our theoretical yield is 16.7 grams, and then we multiplied this fraction by 100% to get our percentage. Okay, so when we divide 12.21 by 16.7 and multiply by 100, we get 73.1138, and that's a percent. Okay, the grams cancel out. The only unit we really have is this percent, which means per 100 pieces. Okay, so 73.1138, well, we want to round this. Okay, because again, we need to consider significant digits. Well, these are my two givens. This one came from the math above. This one came from a measurement. Okay, the math above came from measurements as well. So whenever we are dealing with measurements, we need significant figures. We cannot ever be more precise than our measurements were. Okay, so this one has 1, 2, 3 significant figures. This one has 1, 2, 3, 4. And since we are dividing, our answer needs to be consistent with the measurement that has the fewest significant digits. So that's 16.7 with 3 sig figs. We're going to round this to 3 sig figs as well. So again, start counting from the left, ignoring any zeros on the left. We get 1, 2, 3, 73 point, and I'm going to round to the tenths place using the hundredths place. So the 1 rounds the 1 to a 1. 73.1%. That is our students' percent yield. And that's fairly decent for a high school laboratory. Excellent. Okay, thank you very much. If you have questions, please don't stop learning and find some help. We are always here for you.